10? You mean like constant, always 10? Yeah, it's always 10, because no matter where you put this rectangle, this edge is always touching the y-axis, right? And that means that the distance is going to be from here to here all the time, and that's 10. Right? Chris, you're looking... If I put a rectangle there, isn't the distance from here to here still 10? Put a rectangle here. Distance from here to here still 10? Yes. So in this particular picture, that radius is fixed. So R out is 10. Good, Michelle. Now, inner radius, Jonathan, is from the, where did I put yours? Okay. Oh, here you are, Michelle. Jonathan, inner radius is the distance from the axis of rotation to the inside edge of the rectangle. Do you have an idea of what that is?
10 minus the 2 root y.
Perfect. 10 minus 2 root y. 10 minus 2 root y. And that's using the fact that we know that the distance from here to here is 2 root y, right? Because that's what the curve is. 10's the whole way, so we want to take away that 2 root y. Good. And now we go to the formula, right? Our limits of integration, have they changed? By the way, the reason I'm using less, like my picture's not as good as my previous one, is because we already did this problem a second ago. If this were like the first time I'm putting this up here, I'd show a little more detail. I'd like label all my graphs and everything else. So formula, pi. Stephen, what do you got?
10 squared, 100 minus 10 minus 2 root y squared.
dy. And integral is going to go 0 to 9. So outer radius squared minus inner radius squared. And remember, you would actually have to square this, right? Like FOIL it out, like expand it. But if you did that, this would be pretty straightforward integral. There's no integration by parts, there's no trig sub or anything like that happening in this particular problem. All right, so what do you think I might ask next? Well, I'm not going to ask you for a picture. Yeah, I mean, it's not that important to me that you draw this three-dimensional object. But I'm saying if I were to ask you another question based on the same picture, what do you think I'm going to ask you to rotate? Where do you think I'm going to ask you to rotate it around this time? Something on the other side of it, okay? So like, we rotate around the y-axis, we rotate around a line on this side of it, now maybe a line on this side. So something like x is, let's go with -4. Are you catching on to this? Okay. So I'm going to go with my picture again. Quick though. Picture, boom, rectangle, boom, axis of rotation here at -4. Every time I draw this thing, I bring my axis down, my rectangle down, my axis of rotation down. And we have Gabriel. Where's Gabriel? There you are. Are you following this, Gabriel?
Yeah.
Okay. I'm going to ask you right away for the outer radius. That's the distance from here to here. What do you think?
It's going to be...
What is the distance from here to here?
That would be -4 and then plus 2 root y.
2 root y. Okay, so now the -4, you got to be careful here. You want to always look at this distance as a magnitude, like a distance. So use 4 instead. So 4, and then add to that, you said 2 root y. Everyone follow that? I didn't label it here, but the distance from here to here we know is 2 root y. And then the distance from here to here is always going to be 4, right? So 4 plus 2 root y, that's our outer. 4 plus 2 root y. And then what about the inner, Luis? Inner radius. Distance from the axis of rotation to the inner side of our rectangle. That's the distance from the y-axis to the thing is 0, but from our axis of rotation to there, 4 always, right? Just never changes. There we go. So for this one, everything else stays the same. It's just these guys change right here. All right, so let's go and do, I forgot, 4 plus 2 root y, that quantity squared, minus 4 squared. Still go from 0 to 9. Still have a pi out there, still with respect to y. What do y'all think?
Pretty neat.
All right. So I'm now going to put up a problem on the board, and let me think about it first. Let me think. Hold on. No, it's not a quiz. What the hell are y'all doing? I'm not giving you a quiz. Dad.
Well, you gotta give
Did I say quiz?
You gotta give disclaimers, because.
Oh, did it sound like quiz? Oh, it did? No, I didn't.
PTSD from that.
I didn't mean that to. No, I just want this to work a certain way. Hold on.
Although those take-home quizzes are pretty cool.
Okay, so you know what? Instead of me giving you a problem, I was going to give you a problem to try and motivate the idea, but I think I'm just going to just jump into it without a problem first. So just to kind of clarify, if we have this scenario, function of x, region between the two, we should have no problem rotating that around the x-axis. Agreed? Because we can draw a rectangle in here using washers. Our axis of rotation and our rectangle will be perpendicular, and we can use the method. I should be able to rotate this not only around the x-axis, any line above it and any line below here, right? I should be able to rotate using this whole idea of outer and inner. Yes? But what if I asked you to rotate that around the y-axis? What would be the problem, the way it's drawn up there? Yeah, if you're going to go around the y-axis, right, using washers, then your axis of rotation is this way, which means your rectangles have to be that way. But that's a problem because these, the way they're drawn, are functions of x, but not functions of y. So you couldn't use a rectangle this way because your top and bottom wouldn't be the same, kind of like we talked about in class last time. Do you see that would be problematic to go around the y-axis with this picture? So we have another method that will address that. If I want to go and take this region and go around a vertical line, whether it be the y-axis or something over here or something over here, we use a thing called method of shells. And sorry, I don't have any fancy notes for this right now. Not to say my notes are fancy. Okay, I do have one, I just didn't look it up and I don't feel like looking for it right now. And plus, I like to just do it on the board, it's just more fun for me. Okay, so method of shells. So the method of shells goes like this. If I wrapped that around the if I wrap that right now around the y-axis, okay? If I wrap that, what would it look like if I took that rectangle and just wrapped it around? It would look Yeah, kind of like a washer, yes. I mean, it is a washer, but it's really tall and really narrow. Now, do you remember us looking at that picture earlier? And I intentionally said, let me get to that later, right? Okay, it's because it belongs to the other method, so I didn't want to mix it up with what we were talking about. So we've got this thing, and that thing has a volume to it, right? That thing has a volume to it, and we need to figure out what the volume of it is. And we could look at it as like pi outer radius squared minus inner radius squared times height. We could, but I want to look at it a slightly different way, right? Here's the way I want to look at it. I would like for us to take some scissors, and I'd like for us to cut this thing open, all right? So if I take that and cut it open and lay it out flat, I'm going to get that, right? So I cut it, imagine this is flexible, cut it, and just lay it out flat. That's what I would get. All I can think of is a cinnamon roll. You ever have a cinnamon roll and you like peel that layer off the outside? Imagine just laying it down.
It's almost lunchtime.
Right? Yeah. Right. So this, do y'all see this? Anyone have a problem with this right now? Because if you don't see that, then we need to resolve it. Martin, you're looking kind of strange.
Or the fact like the inside is the circumference is smaller than the outside circumference, we're just making them equal in this picture here.
What are you talking about? What?
So like if I have a circle, right, and it has
Uh-huh.
thickness to it, the
Yeah.
inside circumference, right, that would be smaller than the outside, right?
Yeah.
So when you lay it flat, one side of that rectangle is going to be shorter than the other.
I see what you're saying. Okay, yes. All right, so what Martin is suggesting is that because there is thickness to this, when we lay this out, it's not going to be exactly like a box, so to speak. Do you all agree with that? We're going to have slightly longer, let's say that's the back, the outside, it'd be kind of flared out. Is that what you're saying? Yes, we would have to account for that if it weren't for the fact that the width of this, right? The width of this is what for us? dx. And dx is the width of our rectangle, right? And dx in the limit is going to go to what? 0. And then that won't matter anymore. So great observation, but not going to matter because it's going to dx, because of dx and it's going to 0. Okay? Very good. So now this width is dx, right? Okay, so that's what I was, that right there is dx, right? This thing wrapped. The width is dx. How tall is it? How tall is this thing?
All right.
Yeah, off of this picture, it's this top function, right? It's the top function minus the bottom function. So I could put f of x minus g of x, right? But I'm not going to put f of x minus g of x. I'm going to put top minus bottom, okay? Because I don't want you to memorize the formula again. So this is going to be your top function minus the bottom function. Yes? Sure? How long is it? Okay, pay close attention to this next piece. How long is this thing? It depends on how far away that shell was from, like when we drew the rectangle, right? It's going to vary. It's going to vary. Like if that rectangle would have started here, then it's not going to be as wide, right? Which means when I cut it open, it's not going to be as long. But if I do this one out here, then it's going to be very wide, and when I cut it open, it's going to be very long, yes? So where I am matters, right? And where we are is always x. Remember, when we do an integral like this, we're letting x go from like a to b, right? We're starting at a and we're ending at b. But some arbitrary point in between is x. You follow? So the distance from here to the arbitrary rectangle is x, which is the radius of that thing. From here to here. And I'm going to go to like the center of it. This is what Martin was bringing up, is that there's a thickness to this, but because it's dx, it's going to go to 0. This right here is x. Okay, now is the time to ask questions, okay? Because after I get through this, we're just going to start plowing through the examples. You need to understand where these things are coming from. dx is always the width, thickness of the shell. The height of the shell is always your top function minus your bottom function. The radius of your shell is always the distance from the axis of rotation to your rectangle. So I'm not going to label it x. See, because if my axis of rotation was out here, wouldn't my radius be bigger? So I'm not going to label it x. I put it x here because I wanted you to see first that it's x in the picture. But this is actually, I'm going to call this, what do I usually call it in my notes? I forgot what I call it. I'm just going to call it r.
Radius.
Yeah, for radius. God, I can't even draw a damn r right now. r. But this is the distance from the axis of rotation to the rectangle. So if we know the radius of this, how is that going to give us this length? It's the circumference, right? We take that shell, right? We cut it open, lay it flat. Distance from here to here is equivalent to the circumference of this thing when it started, right? So what is the circumference? What is the circumference of a circle? 2 pi r. 2 pi times the radius. That's your circumference. So then the volume of this one shell, will be the volume of this thing, which is this times this times this. So 2 pi times r times top minus bottom dx. That's the volume of one shell. And how do we get the volume of the whole thing? Do the integral. Where are we going to start? A to B. And then that formula, right? And I'll pull the 2 pi out. That's kind of like your formula for shells. For shells, your rectangle and your axis of rotation are parallel, right? Washers, your rectangle and your axis of rotation are perpendicular. So what's going to happen is you're going to be presented with a problem. You're going to be told to rotate a region around a certain line, and you're going to have to say, well, should I use washers or shells? What's better suited for this problem? You have to make that determination. Nobody's going to tell you, use washers, use shells. Sometimes you can't use shells, you have to use washers. Sometimes you can't use washers, you have to use shells. You have to kind of distinguish between those two. Does that make sense? All right. Let's do an example. Okay, find the volume if you rotate one arc of sine about the y-axis. So basically this. Look at your sine function. Just take one arc of it, rotate around the y-axis. Give me the volume of that. Now, what's kind of implied here is that I'm talking about this region. Okay, I'm talking about that region right there. So if I want, I could add y equals 0, just so you understand. It's closed off there on the bottom. Okay? Rotate that around the y-axis. Washers or shells? Shells, right? Why shells? So if I'm going to rotate around the y-axis, right? If I try and use washers, right, I'm going to be doing, I have to do perpendicular rectangles. Problem with that is you have the sine function, it's the same function, right? So I don't want to do that. I'd rather have my rectangles this way because then I have a clear top and bottom function, don't I? So because my rectangles fit in here better this way, I'm going to be using washers. Oh, shit. Shells. I'm just going to confuse you now. Shells. All right, my axis of rotation is here, here. Now, what I like about shells is that you don't really have to have a whole lot of other pictures. All right? The general idea behind shells, it's 2 pi integral a to b, your radius, and then top minus bottom. I'm going real shorthand now here, dx. All right, so do we know the top and the bottom? Yeah. Do we know a and b? Well, first arc of sine goes from 0 to pi. Okay, so let me start filling some things in here. 2 pi, 0 to pi, and then the radius. Now, what did I say the radius was? Distance from the axis of rotation to the rectangle, which for us is just x, right? That's the x-coordinate. That's the x-coordinate. So it will be for us in this problem x. And then the top function, what's our top function? So what is the top of this rectangle? Sine x. And minus the bottom function, 0, and then dx. Understand? So this is just 2 pi, integral 0 to pi, x sine x, dx. Could you do that integral? Integration by parts. Let u be x, let dv be sine x, dx, and then do your little integration by parts table, and it should work out. That make sense?
Question.
Yes.
Is it paramount to change it to x, or can we just use r?
Well, you have to change it to x because you're integrating with respect to x. So at some point you have to change it to x. Let me adapt this problem just slightly. Okay? Find the volume. If we rotate one arc of sine about not the y-axis this time, I'm going to go about x equals -2. So I've moved my axis of rotation, not here, but over 2. So now my axis of rotation is here. You'll see the difference between these two? Does the top and bottom function change? Top and bottom function? Is the top still sine? Is the bottom of the rectangle still 0? Okay, that's fine. The only thing that changes is the radius, which is the distance from the axis of rotation to the rectangle. That's the distance from here to the rectangle. We know the distance from here to here is x, but now we have to tack on to it what? 2, plus 2. So from here to here is 2. So the entire distance from here to here is 2 plus x. And it's not 2 minus x, right? Because, again, we were looking at that as a distance. That's the only thing that's going to get tweaked in the problem. The only change is that this x becomes 2 plus x. That's it right there. Does it make sense? What about x equals, let me go to the other side. So I got to go past pi. So I'm going to go to like 6. Same region, right? Same region, same picture. 6 this time. But now I definitely want to stick with shells, right? Perpendicular. So axis of rotation here. So now what we need to do, top and bottom don't change, but our distance from the axis of rotation to our rectangle is now this distance from here to here, which I think I already heard what it is. 6 take away x, right? This is 6, this is x, this is 6 minus x. Not x minus 6, 6 minus x. So that would change this right here to 6 minus x. Yes?
There's no inner or outer because of a gap.
There's no inner or outer because of a gap. You mean the width of this
Well,
gap?
for the arc to 6, there's no inner.
Yeah, the washer is where you have an outer and an inner. The shell, you just have a top and a bottom. That's it. I like shells. Shells work, whenever I can do shells, I do shells because they're just, the setup to me is easier, but it's, it's all relative, right? It's all relative. So what I like to do on tests, right, is I'll give you a region, right? First question on tests is usually, sketch the region bounded by these curves, find the area between them. So that's from the last section. So you have to do that right and do it all, draw your picture perfectly. Then I'll have the next question will be, all right, for the region you just found the area of, rotate it around the x-axis, rotate it around the y-axis, rotate it around x equals 5, x equals negative 5, y equals negative 4, y equals 10. I'm going to give you one region that I want you to be able to, like in theory, right? In theory, if I give you a region now, whatever it is, you should be able to wrap this around the x-axis, right? Y-axis, lines here, 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 here. So I can have one region and ask you basically like what? Like a bunch of different questions, right? Yes?
Are you ever going to have where we have 2 regions?
Nope. Oh, you mean like maybe it would do like something like this and then come back again and do both of these? No.
Very gracious.
Unless you're requesting.
No.
Yeah. Yes.
Is there a formula, like once you know the area of it, to then just use that number to get a rotation volume?
If you know the area, to then know the volume if you rotate about like an axis?
Is there a formula to go from the area of a region to then that region rotated?
Well, what do you think?
I think yes.
You think yes? Okay, so trying to think of a way that you could.
Because if you have a cylinder, you know the area of one, you can get the whole thing.
Mm-hmm.
But if you have a right toroidal disc.
You're saying if you're given if you know the area and you know the axis of rotation,
Yeah.
is there a formula for that?
Yeah.
Yeah, I think you could come up with something. I mean, you could,
Because that way we can always find the area the same way and then just.
regardless of, yeah, but it would all be based on the axis of rotation, right? Yeah, I'll look, yeah, because the whole idea behind a volume is this. Like if you know the area of some surface and just project it down and get some depth to it, then the volume is just this area times whatever this height is. So that's how you can find, so what you're saying is if you find the area, then if you wrap that around any axis, right?
Yeah.
Cut that open and lay it flat, you have one of these basically.
No, because it doesn't work that time because then it's not the actual will matter with that difference.
I'm just saying arbitrarily. Like if you wrap an area around an axis, whatever that object is, if you were to be able to cut it and lay it out flat, you would have something like this. And the volume of that would be the area, of the surface area of a cross-section times the length of it. And that length would depend on the axis of rotation. There's probably a way you could come up with a formula, but I would argue that maybe just the Shell's method and the Washer method is just as efficient. And I don't think you can get away from the integral. I think you'd have to have the integral somewhere. Yeah. Okay. Well, we're not done. This section still has a little bit more in it. Y'all all right? You know what? Yeah, you've got, what, 10 minutes left? I don't think I should start the next part. I think this is enough for you to swallow for today. God, it's crazy that this section is only like 2 pages. It's just crazy that the book just wants you to read this and be like, yep, got it. I should warn you, we're going to just cut it today. We're just going to stop. But I will warn you, I mean, if you do go to the tutoring lab or something, or you've got a friend who knows how to do this and you're getting help, like, I can guarantee you it's not going to look the same as this. Like, it's going to look completely foreign. And I can always tell on a test the people who have, like, found someone who knows they do it a certain way. I won't dock you for that, but I'm just warning you ahead of time. Like, if you go to someone else, you're going to be relearning it, basically, a different way. All right? Okay.
I had a theoretical question.
Yeah, we're done. Next week, we'll have a quiz. That was requested.
I didn't request nothing.
There was a request for a quiz on a double region.
Not me. I requested a take-home quiz.
Yeah. Pardon?
Is the exam graded?
Oh, yeah. Where you been? You weren't here last time? Yeah. Okay. Let me turn off my camera. Tavia, right here. That's it. Uh-huh.